morning, everybody. My name is Maria del Carmen Perez. I'm a chemical engineer. I'm working by Audible Sugar Institute. And today I will be talking about how seasonal sucrose losses varied across clarification in 3 Louisiana sugarcane factories during 2019 season. Why this study? The sugarcane production process, a major source of chemical sucrose losses occur during the clarification operation. And when we talk about clarification, we are also, sorry about that.
Go back one.
When we talk about clarification, we are always thinking about clarifier. But clarification operation have 2 main parts. One of them is the clarifier, and the design and operation have a great influence in the performance of the operation and the sucrose losses, but also another important part are the peripheral operations. When we talk about peripheral operations, we're talking about liming, temperature, and flocculants, preparation and addition, and the flow controls between others. A comparative investigation among 3 sugar factories in Louisiana with different type of clarifiers using high retention time clarifiers that we called HRT and short retention time clarifiers that we named SRT. Was undertaken to evaluate their performance across the 2019 processing season. In Factory A, we work with 2 HRT clarifiers that we named HRT1 and HRT2 with 75 minutes of retention time each of them. In Factory B, we was working with 3 different types of short retention time clarifier, and instead you can see here that both 2 of them are LRT clarifiers. They have different technical design. Because of that, we can say that we have 2 different types of clarifier here. The retention time was 48, 50, and 54 minutes. Factory C, we work with 1 SRT clarifier for the use to process the use from the diffuser side of the factory with 60 minutes of retention time, and 1 HRT clarifier to process the use from the tandem mill, another side of the factory with 90 minutes of retention time. Now, samples of these different materials were collected. We collect hotline flash juice. We collect clear juice, and in the case of Factory A, we collect also mud. 5 samples of this material were collected per day, and in the case of the clarified juice, the clear juice, the retention time of the clarifier was taken into account. 5 samples of each material were collected per day with 30 minutes interval between the sampling. And the sampling periods were repeated across the season for each factory, having at least 8 visits to each factory, and in the case of the Factory C, 8 visits to each side of the factory. The clarified retention time was calculated from the use volumetric flow rates and the mood and use value on the clarifier, although it was necessary to set the value for the retention time due to high variation. The sample was immediately frozen in dry ice after collection, and after transportation to Audubon Sugar Institute were stored in a -80 C degrees freezer under analyzed. One of the main points of this study was the calculation of the sugar losses to all the materials collected, and the sugar losses can be calculated to these 2 formulas. One based on the sucrose loss based on glucose increase, and the second one on the percent of sucrose loss based on sucrose decrease. The calculated pounds of raw sugar loss per ton of can was also calculated, taking into account the price of the sugar at this time. The analysis that we made, that was performed of all the samples was the bricks, pH, turbidity, calcium and phosphorus, sugar, glucose and fructose, and in this case, all the analysis have a duplicate, and the sedimentation rate and mood volume of all the uses. To perform this analysis, we use all of this equipment that we have at Audubon Sugar Institute laboratories. Now we're going to be talking about the result obtained of this study. The sucrose losses, as you can see here, higher sucrose losses are expected at the beginning of the season. However, this behavior was only observed in the case of the factory A. Factory B and factory C had a very variable sucrose losses through the season and greater than the factory A. Here we have the different type of clarifiers used and the retention time of each of them and the seasonal sucrose losses %. And we can see here that in factory A have no significant difference in the sucrose losses between the two HRT clarifiers with 0.249 and 0.201% in each respectively. Factory B, it was surprisingly higher losses than in factory A. Instead, the clarifier have less retention time. And the sucrose losses on the Fletcher clarifier were lower than the losses in the LRT clarifiers that with values of 0.21 in the Fletcher clarifier, 0.336 and 0.363 respectively in the LRT clarifiers. And in the factory C was also no significant difference between the losses. Instead, we are using an SRT clarifier in this side of the factory and an HRT clarifier on the second part of the factory. Comparing the three factories, mean sucrose losses in factory C was higher than the factories A and B, with 0.49% in factory C and 0.227 and 0.266 respectively in factory B and C, A and B. The results show us that similar sugar losses in clarifier was completely different, with clarifier with completely different designs and retention time, which demonstrate us that there are other parameters, for example, the pH control, use, purities, and temperature that have great influence on sugar losses during clarification, like I was talking before.
Next one.
These sucrose losses have an economical impact for each factory, and we can see here that the greater losses have great economical impact in factory C. Also, we can say here that this is that these losses was the total losses for both parts of the factory. Factory B instead have low retention time clarifiers have great losses than in factory A. And it means that when we talk about clarification efficiency and sugar losses, we can look not only to the clarifiers, we can look at another parameter that have influence in the sugar losses. The sucrose and glucose content, we can see here that the factory C had the lowest juice purity with the high variability and the highest glucose and fructose content. High glucose and fructose contents indicate cane juice deterioration, which accelerates sucrose losses in the factory due to acid formation. In the case of pH, we have to say here that factory A is the only factory that have a target pH on hotline flash use. Factory B and factory C have the target pH is on and clear juice. Factory B and C do not have a target pH, as I say, because the control is over the clear juice pH. The use of a liming was common factor in factory A and C, which could increase the color generation and the scaling in evaporation. The removal of calcium in the juice clarification was between 24 to 46%, which means that the rest of the calcium remained the clear juice, like we can see here. And it means that for some reason, the liming process and the pH control was not working really good in these factories, and the clarification reaction were not complete. The turbidity remover is an important it's very important to evaluate the clarification performance. As we can see here that the factory A have the higher turbidity removal, the higher percent of turbidity removal, and factory in the main season turbidity removal, and the factory followed by factory B, and at the end factory C. Now we talking about the conclusion that we could have the result of based on the result of these studies. In all the three factors, common denominators that we found were the variability of the use flow entering the clarifiers, which have a great effect over the clarifier performance. Also, this flow use variability made difficult to control the flocculant dose, the use temperature, and the use pH, with the last one evident by the 38 to 55% of the use samples analyzed having pH values higher than the target pH of the factories. Additionally, the factories did not have control over the preparation, like a density of the solution and the addition of the flocculant solution to the juice. And the solution was added at the point where an homogeneous mix with the juice was not assured, which have a great influence on the clarifier performance and on the sucrose losses. Highland consumption was also common, and the overheating of the juice. The behavior of the sucrose loss in the sugar factories cannot be attributed only to the type of clarifier of the recent time. As I told before, in the two parts of the clarification process, the peripheral operation have a great influence not only on the clarifier performance, but also on the sugar losses, as could be seen in this study. Comparing the three factors, mean sucrose losses in factory C were higher than factory A and B, which value from 0.429% and 42.7 and 42.66% respectively, due to lower juice purities and high glucose and fructose context. High reducing sugars indicate cane juice deterioration, which accelerates sucrose losses in the factory due to acid formation. Sucrose losses can be also reduced, increasing the clarification efficiency and ease peripheral operation, especially by having an optimum target pH and a strong temperature and pH control, among others like the flocculants, preparation and addition, the liming process. And when we talk about liming, we are talking about the purity of the lime, the water used on the lime preparation, and the point where the lime is added to the juice that should allow the proper time of with the juice, the lime and the juice, and that can allow us to have the great clarification process. Further studies are necessary to identify all the factors that are affecting the sucrose losses in factory C, and also it's going to be good to change the reasons of this or of this variation on the pH and temperature in the three factories, and to repeat the study to see how these factors can reduce the sucrose losses to the factories. We want to acknowledge, we want to say thanks to the American Sugar Cane League for the partial funding. We want to say thanks to all the factory staff and management for their help. We want to thanks to all the collaborators in this study and to say thanks to Dr. Eggleston for all the support and excellent guide during these studies. And thanks to all everyone, to listen to us today.